In this video, we will derive the truth table based on a given logic circuit, and then we will construct a logic circuit based on a given Boolean expression.
Now we conduct our experiment.
On the given Boolean expression, x is equal to the quantity of x bar plus y, ANDed with quantity x plus y bar complement. We derive the truth table based on the given expression, and we consider the first two columns, x and y, as the inputs. And since there are two inputs, the possible number of output is 4. The next column is for the complement of x, which is denoted by x bar. From 0, it becomes 1. And from 1, becomes 0. And that applies to all. The next column is for the expression x bar ORed with y. We compare those values, and the result becomes when y is 0 and x bar is 1, it is resulted to 1. When y is 1 and x bar is 1, the result is 1. When y is 0 and x bar is 0, the result is 0. When y is 1 and x bar is 0, the result is 1. On the next column is the complement of y, which is denoted by y bar. So like what we did from x bar, we compare the value of y, and from 0, it becomes 1. From 1 becomes 0. That applies to all. On the next column, x plus y bar and its complement. When x is equal to 0 and y is equal to 1, becomes 1. But due to the complement, the result now would be equal to 0. Another, when x is equal to 1 and y bar is equal to 1, the answer is equal to 1. Due to the complement, it will be equal to 0. And that will repeat all the process. For the output S, the result of quantity x bar plus y and the complement of quantity x plus y bar is ANDed. So to get the output value in an easier way, we compare the two columns and look for the row which have 0 values. The output for this will be automatically 0.
Now we construct our logic circuit. We are given the equation S is equals to quantity X bar plus Y ANDed with quantity X plus Y bar complement. And I will label this as the first expression and this one as the second expression. Now let's draw the first equation. First, we connect our X input to a hex inverter because it needs an X complement. And since it's plus, we would just connect our Y input to the output of the X inverter connected to X via an OR gate since it's plus operation. Connect it here to an OR gate. There. For the second equation, we will need our X input and since it's a plus sign with the bar all over the quantity, it would be a NOR gate. We connect again our Y to an inverter and connect it to a NOR gate. Now for our S, we just simply connect our first equation and our second equation to an AND gate since no plus sign is in between them and two parentheses meeting each other, meaning that it will be ANDed or multiplied. Now we have our S. Now, it's time we do it on a breadboard. We first connect our inputs X and Y to pins number 1 and 3 respectively of the inverter IC. Next, we connect the pin number 2 of the inverter to the pin number 1 of the OR gate. Then, connect pin number 3 to the second pin of the OR gate to get the first expression X bar plus Y at pin number 3 of the OR gate. Next, we connect pin number 4 of the inverter to the pin number 3 of the NOR gate since NOR gates operate by starting the output then followed by the two inputs. Then, we connect pin number 1 of the inverter to the second pin of the NOR gate to get the second expression quantity X plus Y bar at pin number 1 the NOR gate. Then connect pin number 1 of the NOR gate to pin number 1 of the AND gate and connect pin number 3 of the OR gate to pin number 2 of the AND gate to get the total expression which is quantity X bar plus Y ANDed with quantity X plus Y bar complement at pin number 3 of the AND gate. Now, it's time to check the output at the given input combinations. The first combination is X is equal to 0 and Y is equal to 0. Just connect the two hanging inputs to the negative source and the output we got is 0. For the next combination, we connect Y to the positive and the X remains on the negative. The output is 1. We then switch their position, then record the value which is 0. For the last combination, we connect both inputs to 1 and record the value which is 0.
Moving on to the next part, we are given the Boolean expression F is equal to the complement of quantity A plus the quantity of A NANDed with B and then ANDed with C. and plus the complement of A bar ANDed with C bar. To derive the theoretical table, we consider the first three columns for the input variable ABC. The next column is for the A bar. Complementing A, from 0 it becomes 1. From 1 becomes 0. Applies to all. The next column is for C bar. When Z is equals to 0, becomes 1. And when C is equals to 1, becomes 0. On the next column, it is the A NANDed with B. So, we consider A is 0 and B is 0, it equals to 0. But it is ANDed, so it will now be resulted to 1. Next, when 0 is ANDed with 0, it becomes 0. But due to the complement, it becomes 1. And it applies to all. On the next column, A plus the NANDed result of A and B. When A is equals to 0 and the NANDed result is equals to 1, the result is equals to 1. Observe that whenever there is a 1 in the row, the result would always be equal to 1. On the next column is the expression complement quantity A plus the NANDed A and B and NANDed with C. So, C is 0 and anything ANDed with 0 would be equal to 0. But since the expression has a complement, the result from 0 is now equal to 1. Next, we get values of C and we obtain 0 as well. So anything ANDed with 0 would be equal to 0 and complementing it would be equal to 1. For the next column, it is A bar ANDed with C bar. When A bar is equals to 1 and C bar is equals to 1, the answer would be 1. And since there is a complement in it, the result from 1 will be equal to 0. When A is 1 and C bar is equal to 0, the answer would be 0. Complementing it, the result from 0 is equal now to 1. Repeating the process. For the output F, it is said to be that the last two columns is ORed. So anything ORed with 1, as we observe in either rows, would always be equal to 1.
Now, it's time to create again an LOGIC circuit. You are given the expression F is equals to the quantity A plus quantity A NANDed with B. Quantity C complement plus A bar times C bar complement. Now we'll just label our expression, and I'll label this as my first equation, this one as my second, and this is my third, and this one as my fourth expression, and our output F as our fifth equation. First, we will draw our first expression. we would need to connect our A and our B to a NAND gate. Yeah. Then, now it's time to do our second equation. Connect our A to an OR gate with the product of the NAND gate. And our third equation, connect our input C with the output, the A plus AB complement to a NAND gate. Next, for our fourth equation, we would connect our C input to a hex inverter. Also, we would connect our A input to a hex inverter to a NAND gate. Since it is a 1 tap, we would connect it to a NAND gate. For our final output, we would connect both final equations. Since that is plus, connect the left side of the expressions to the right side of the expressions to an OR gate since it has a plus, and that's a logic circuit. As you can see, this is our first equation, and this is our second equation. This one as our third equation, this as our fourth, and this is the output, the fifth equation. Now, it's breadboard time! First, we connect the first pin of the inverter IC and set it as our A input. Next, we connect the third pin of the inverter IC and set it as our B input. Then, connect the first pin of the inverter IC, which is A, to the first pin of the NAND gate. Then we connect the third pin, which is B, to the second pin of the NAND gate. Now we get the input of A NAND B via the third pin of the NAND gate and connect it to the first pin of the OR gate. Again, we connect our A, which is the first pin of the inverter, to the second pin of the OR gate. Then connect the third pin of the OR gate to the fourth pin of the NAND gate. And now we will set the fifth pin of the inverter IC as our C input. Get our fifth pin and connect it to the sixth pin of the NAND gate and get the output of that via the seventh pin and connect it to the 15th pin of the OR gate. With that, I'm now gonna then we get not A, from the second pin of the inverter IC and connect it to the 15th pin of the NAND gate, and get the NOT key via the 7th output pin of the inverter IC and connect it to the 14th pin of the NAND gate, and get the output of that in the 13th pin, connect it to the 14th pin of the OR gate. Now we will record the value of the output at pin number 13 of the OR gate. Then we set the inputs A, B, C to 0, 0, and 0 respectively, and record the value which is 1. And now set it to 0, 0, 1, change it to 1, and record the value which is still 1. Change the input to 0, 1, 0, and record the value 1. Change the input again to 0, 1, 1, and record. Change again to 1, 0, 0, and record is 1. Change the combination again to 1, 0, 1, and record is 1. Record it to 1, 0, and 1, which is equals to 1. Lastly, set all the inputs to 1. You get all 1. Thanks for watching.